Have you ever wondered how the ancient Egyptians built the pyramids without modern technology? No cranes, no computers, no laser levels. Yet, the Great Pyramid of Giza stands as a monument of impossible precision. Its base is a near-perfect square, with sides over 230 meters long, differing by just a few centimeters. How did they achieve this? The answer isn't magic. It's math. Ancient algorithms, hidden in plain sight. Today, we're decoding the mathematical secrets behind one of humanity's greatest engineering marvels. Let's start with the basics. The shape. The Great Pyramid's base isn't just a square. It's an almost flawless square. Imagine trying to draw a square that big today, even with all our fancy GPS and surveying tools. Getting it right would be a massive challenge. The Egyptians managed this feat over 4,500 years ago. How? One popular theory involves a simple but brilliant tool, a knotted rope. By creating a rope with 12 equally spaced knots, they could form a perfect 3-for-5 right-angled triangle. This is the Pythagorean theorem in action, thousands of years before Pythagoras was even born. By repeating this process at the corners, they could lay out a massive, precise square foundation. This wasn't just construction. This was applied geometry on a colossal scale. But the precision doesn't stop at the base. The pyramid is also aligned with incredible accuracy to the cardinal directions: north, south, east, and west. We're talking about an alignment with an error of less than 1/10 of a degree. To put that in perspective, many modern buildings aren't that precisely aligned. The Egyptians likely achieved this by observing the stars. They might have tracked the movement of a single star as it rose and set, bisecting the angle to find true north. This method, known as the pole star alignment or the circumpolar star method, would have required patient, meticulous observation night after night. It's a testament to their understanding of astronomy and their ability to translate celestial observations into earthly engineering. Now, let us get into the really mind-bending stuff. The hidden numbers encoded within the pyramid's very dimensions. If you take the height of the Great Pyramid and multiply it by 2 pi, you get a number that's incredibly close to its perimeter. Let me say that again. The relationship between its height and its base perimeter mirrors the fundamental mathematical constant pi, the ratio of a circle's circumference to its diameter. How is this possible? Did the ancient Egyptians know the value of pi? It seems unlikely they had the decimal value we know today, but they clearly understood the geometric relationship. They might have discovered it empirically, perhaps by using a rolling drum or a wheel to measure distances. A measurement like 22 cubits around and 7 cubits across gives a very close approximation of pi. It suggests a deep, intuitive grasp of geometry that goes far beyond simple shapes. And it doesn't stop with pi. The golden ratio FAI, approximately 1.618, also appears to be embedded in the pyramid's design. This divine proportion is found throughout nature, in seashells, flowers, and even the human body. It's often associated with aesthetic beauty and harmony. In the Great Pyramid, if you take the slant height of one of its faces and divide it by half the length of the base, you get a value remarkably close to the golden ratio. Was this intentional? It's a hot topic of debate among historians and mathematicians. Some argue it's a coincidence, a natural byproduct of the construction methods. Others believe it was a deliberate choice, a way to imbue the structure with a sense of divine harmony. Either way, the presence of these fundamental mathematical constants in a 4,500-year-old structure is nothing short of astonishing. So we have incredible geometry, astronomy, and maybe even advanced mathematical constants. But how did they actually build it? This is where the idea of ancient algorithms really comes into play. An algorithm is just a set of step-by-step instructions to solve a problem. The Egyptians were masters of this. Building a pyramid wasn't one single task. It was millions of smaller, repeatable tasks, each governed by a clear process. Think about the quarrying of the massive stone blocks. Each block, some weighing several tons, had to be cut to precise dimensions. Scribes would have created plans, essentially blueprints, dictating the exact size and shape of each stone. The workers then followed a procedure, carving channels into the limestone, inserting wooden wedges, and soaking them with water. As the wood expanded, it would crack the stone along the desired lines. This was an algorithm for stone cutting. Then came the transportation. How do you move a 2-ton block from a quarry miles away to the construction site? The most accepted theory involves sledges pulled by large teams of workers over a path lubricated with water. It sounds simple, but it required immense coordination. Every worker had a role, every movement was planned. This was an algorithm for logistics. The number of workers, the amount of water, the pace of pulling all of it would have been calculated and refined over time, and finally, the placement. This is perhaps the most incredible part. The stones had to be lifted and placed with millimeter accuracy, rising hundreds of feet into the air. While the exact method is still debated, most theories involve ramps. Whether it was a single long, straight ramp, a spiral ramp that wrapped around the pyramid, or an internal ramp system, each required a sophisticated algorithm. The slope had to be gentle enough for the sledges, but steep enough to be efficient. As the pyramid grew, the ramp had to grow with it. Every single block's journey from the base to its final resting place was a calculated, procedural step in a grand architectural algorithm. Scribes and overseers acted as the project managers, ensuring each step was executed correctly. They didn't have spreadsheets or project management software, but they had papyrus scrolls, hieroglyphs, and a system of command and control that was brutally effective. This entire process, from quarry to capstone, was a massive real-world computation. Each worker was like a small processor, executing a simple instruction. The overseers were the controllers, managing the flow of data. This case, stone blocks. The master architect was the programmer who wrote the overarching algorithm. It was a human-powered computer executing a program to build a mountain of stone. This is why we can call it an ancient algorithm. It was a repeatable, scalable, and remarkably robust system for achieving a seemingly impossible goal. The proof of this algorithm's success is its longevity. The pyramids have stood for 4.5 millennia. They have survived scorching heat, powerful winds, flash floods, and even major earthquakes that have leveled modern cities. This incredible durability isn't an accident. It's a direct result of the engineering precision. The stable, wide base and the massive weight of the stones create an incredibly low center of gravity. The near-perfect fit of the blocks, with joints so fine you can barely slip a piece of paper between them, distributes the weight evenly and prevents shifting. They didn't just build a tomb, they engineered a structure to last for eternity. The design algorithm included factors for stability, durability, and resistance to natural forces. They were thinking about long-term structural integrity in a way that is still a model for engineers today. So, the next time you see a picture of the pyramids, don't just see a pile of old stones. See one of the greatest computational and mathematical achievements in human history. See the silent genius of knotted ropes defining perfect right angles. See the celestial alignment achieved by watching the stars. See the whispers of pi and the golden ratio hidden in the slopes and dimensions. See the thousands of workers executing a complex step-by-step algorithm to quarry, transport, and place millions of tons of stone with breathtaking precision. The pyramids are not just a mystery of the ancient world. They are a masterclass in mathematics, astronomy, and engineering, a testament to what humanity can achieve with logic, ingenuity, and a very, very good algorithm. Thank you so much for watching. If you found this journey into ancient mathematics as fascinating as I did, please hit that like button and subscribe for more deep dives into the secrets of history. Let me know in the comments what other ancient marvels you'd like us to decode. Until next time, stay curious.